They're trying to diversify.
I probably. And I hope they're like, wow, because of the wage gap, we're gonna actually pay you guys.
Yes, $1 million more per month. I didn't ask though.
All right, how's everyone doing?
Oh, of course, it was good.
Did you end up putting in the press?
I thought about it and then I read yours and I was like, okay, yeah, you're right.
I mean, like, I'm sure that I was just like, if I had to do that, I was already tired. And I was like, I can't add any more to this.
Well, I was literally just gonna, I had a plan to explain it more than I actually did.
Yeah.
But then I realized like I was writing it anyway and I was over the limit already.
Yeah.
And I was like, oh, actually.
Okay, first things first, here's a picture of my adorable child. This is from Friday. We were just hanging out. My wife's a photographer, so like we get all these nice pictures. Yeah, this is what my life looks like these days. She this is her smile, and she smiles all the time, except for this weekend. We traveled to Lancaster, and she did not like the car and did not like the crib we had there. So no one slept well until last night, and then we got a full night's sleep for the first time in a very long time. So I'm feeling great. It's a gloomy day. Here's what we have on deck. We have a bit of work to do to finish binary models, to binary outcome models. So that's what we're going to do at the beginning. And then we're going to talk a bit about ordered models, I think. So we're going to spend a little bit of time just introducing the idea of an ordered model, which is really a simple extension of the binary model, but two cases where instead of just having two things in an order, we have more than two things. There's a bit of extra work, and conceptually I think it is just quite a bit more challenging than a binary model. So what I want to do today is just introduce it as a concept. And then in the back half, this is a good time for us to pause and just go back and think about what we've done so far. We've done a lot, and I think like the way the MQE is structured, we fit a lot of material into a short amount of time. So sometimes I think it's easy to lose sight of the forest for the trees that we're in. And so what I want to do is actually just go back and walk through the checkpoints. We have the first two checkpoints, and what I want to do is just talk them through, which I think will be helpful. The reason I want to do this, we're at a bit of a potential breathing point, just to pause and take a breath. So I think that would be helpful. Yeah, I think I've said this, like, the details do matter, but I think the way I learn and the way I've noticed my students in the past learn best is by focusing on the broad arcs first and then digging into the details. And what we've done with the first two checkpoints primarily, but also the third one, is really cover the whole scope of what we've done in the first part. And it fits under a pretty big sort of unified umbrella. We do this, we cover these topics in this way because it is a unified idea. So I just want to go back and basically just cover everything from the perspective of the checkpoints. Does that sound like a plan? A real chance we might get out early. I don't want to promise it. But I think last class, we took a 4-minute break instead of our 8-minute break. And I promised you a second break last class, and we did not take it. So I owe you 4 minutes, so we'll see how that goes. Y'all do anything fun this weekend? No?
I played some tennis.
Okay.
That was exciting.
The weather was nice here, I guess.
Saturday, yeah.
Okay.
Not Sunday. I mean, it wasn't bad.
Was it rainy?
It was just kind of cloudy and a little bit colder. Saturday was like sunny and really nice.
Yeah, nice. Yeah, we were in Lancaster, and it was like a shot from like a scene where the characters are in a movie where they're in heaven, just like green grass and like light through the trees and like little insects floating around. So tennis. What else?
Golf.
Okay. You mentioned the U.S. Open.
The Masters.
Masters. Oh yeah. We drove past Bakery Square on our way back in, and there's that big TV, and they were playing golf, and I thought of you.
Thank you.
Yeah. So some golf. That's nice. Any extra sleep? Do you get extra sleep over the weekends? Okay. Okay. I think I told you I did not. But it was about the worst sleep I've had in like 0 to 3 month old baby is terrible sleep. Since then it's been fine until this weekend. Okay, you all want to do some work? Like what we're doing, like these are all pretty complicated models, I think. Like they're the core tool set we use in the field is OLS. Sometimes just having the skill in your back pocket sort of frees you up conceptually to be able to think about more challenging problems, which is why we introduce these things before you actually need to encounter them in your work. I think just having the cognitive flexibility to think about estimating models in these ways allows you to approach problems that look very challenging to other people, which is like that's why we're introducing these things. So you'll remember at the beginning of the semester we talked about numerical estimation. So we talked about what happens when we don't need to take the limit we can actually just approximate a derivative using a computer. We talked about simulation, which I think in retrospect, I would maybe reorder these to put simulation first, because numerical estimation leads us directly into nonlinear least squares. So using something like Newton-Raphson to perform an optimizer over a nonlinear function. We're going to come back to this reviewing checkpoint 1, but that was a big departure for us. We also talked about quantile regression, which I think can be useful, but in practice, like I don't think I've ever used it in an estimation procedure. But depending on your application, that can be useful. Maximum likelihood is really where we first started hitting the gas. This was the general optimization sort of approach. It uses nonlinear estimation, nonlinear least squares, sort of behind the scenes to optimize. Like when we don't have a closed form solution, we can just have a computer do a bunch of optimization for us. So we'll come back to this, I think, a little bit in checkpoint 2. GLMs are just a natural extension of maximum likelihood. So every GLM is an MLE, but not the other way around. So GLMs are a strict subset of maximum likelihood, where essentially we're just we define the likelihood function, we plug in our data into the likelihood function, and then we try to maximize the likelihood of our data. So we're going to talk about these things. The last thing we're doing, by last thing I mean first thing, is talking about binary models. So this was our first application of a GLM. We'll talk about a few other things with GLMs. Ordered models are sort of an extension of the binary model to instead of thinking of two things that are ordered, we think of more than two things. But as I understand them, they are not GLMs. They're sort of an extension of some of the ideas we talk about in binary models. For the sake of parsimony, I was trying to, but if you strongly object to this, let me know. There's sort of a natural progression between binary models into ordered models into multinomial models. Originally, I had it set up this way, but then I thought about moving sensory models and selection models because some of you are working on a data set that involves that kind of model. So originally I had thought about moving that earlier, but I think for parsimony, I'm actually going to revert back to the original. If you want to take a look at the notebook, you can feel free to do that. I haven't updated it since last year, so it might look a little bit disjointed, but that's there for you. We will cover it, but I think this order makes a little bit more sense pedagogically. So what we did last class, we introduced, okay, unfortunately we're gonna hide Maxine's cute little smile. So what we did last class was just introduce the idea of a binary outcome model. And the way we talked about this, in GLM, we talked about a binary general linear model. Binary outcome models are really just extensions of the GLM, where instead of having a general model, we have a specific data generating process. So we're just going to set up the data as a binomial. So we're drawing data from the binomial distribution. And what we're doing is just setting up a general linear model, generalized linear model with binomial data. So this was the data set we worked with. So we started thinking about field goal data. So either a field goal goes in or it doesn't. And the idea is that you want to try to make a field goal. So when you're kicking it, you try to make it go in. Behind the scenes, we're going to think of a field goal kick as having a particular quality. If it's greater than 0, then it goes in. And if it's less than 0, then it doesn't go in. So we're going to have like what we call a latent variable behind the scenes, which is one way of thinking about the data. What I've done here is collected from this GitHub site, NFL Scrape R. So this is a bunch of play-by-play data from the NFL between 2009 and 2019. You'll notice we have a lot of short field goals. I think in the modern NFL since COVID, we actually have much longer kicks. So you'll see like 60 plus is not going to be represented in our data. But you'll remember this was our data set. So this was all of the field goals in total. But then what we want to do is focus just on the kicks that were not blocked. So a blocked field goal is not an indication of the quality of the kick. So we're actually going to take it out. It's like the defense did something really well. So we're going to actually pull that out because what we're trying to model is whether the field goal went in due to the offense, primarily to the kicker. And when I run all the data, just plot this out, what I've done here is on the horizontal axis, I have the distance to the field goal. And then the vertical axis is the proportion. So if you're close, I don't know how you would. I think if I were to attempt to kick a field goal at like 3 yards, I would probably miss. But if you're a professional, it looks like basically all of those go in. But then it drops off pretty nicely out to plus 40. So plus 40 is actually very unusual. The size of these data points is the total count at each one of these distances. So you can see the number of field goals beyond 40 yards is pretty unusual. And it looks like these are observations down here. So basically closer to 50 is never made during this period, which is surprising to me. I don't think I was watching the NFL during this time. But today we definitely hit, by we I mean my favorite position in the NFL, definitely regularly hits 60 plus. So I think this distribution would actually be shifted if we were estimating this today. So that's interesting. What we did first was set up a linear probability model. So this was using classic OLS. We're just going to try to predict the probability of success, which is a 1. So what the field goal going in, using how far you are from the how far the kick is, and this is the model. So this is, the vertical intercept is greater than 1. So that's a first red flag. This second thing we have here is the relationship with yards to success, and you can see this is negative, which is exactly as we'd expect. So the further away you are, the worse your kick. And then I'm just going to plot the data with our model. So this is a bunch of binned data, and then we're trying to estimate our linear probability model. And like we showed last time, this is, I think, a terrible model. There are ways we can improve this, and we will. But this is, I think, just horrendous. A couple of things that make this horrendous. First off, it goes above 1. So we're, if you're kicking from the 0, or like the 5-yard line, the probability of success for you is greater than 1, which is nonsense. One thing we can do is censor this. So we can say, if it's greater than 1, we're just going to round it down to 1. But that means our model, like the way we're estimating it, isn't consistent with the way we're using it. So there's some problems there. The other thing is, for very long distances, the probability of success is less than 0. So a negative probability is just not interpretable. So the other thing we could do is just round it up to 0 when we're in that situation. And in practice, we're never attempting field goals at 90 yards. But that's another problem. This data doesn't suffer so much from that problem, but it is a problem with linear probability models. The other thing is that it doesn't estimate very well for these data points. So what do? Well, we've talked about nonlinear models, and we've introduced this as a binary outcome model. So what we're going to do is just focus on estimating models that return probabilities between 0 and 1, which sort of requires us to not build models that are linear. So, because we have to sort of bend the line. So what we're going to do is look at 2 different binary outcome models. One of them is the logit. So this uses the log odds ratio. So the probability of success divided by the probability of failure. And then we're going to take the log of that. And so the link function is going to be this thing. We plug in p, and that gives us our function here. So g is the log of x over 1 minus x. And then we just have our linear predictors on the other side. When we rearrange this, we get this relationship, which is the logit, or sigmoid. And then we also have the probit, which is very similar, like we talked about last time. This is just the inverse of the normal CDF, which, inverted gives us this thing. So both are GLMs. We have a link function. They're invertible. Even though the normal CDF is not tractable, the analytical inverse is not something you can write down. But we can write this. It is invertible, even if you can't write it down analytically. Okay, so these are both GLMs. So what we did is we walked through estimating these two GLMs. We said, here I'm going to estimate, and these have their own names. So I just use smf.logit, and then I put in the model equation, data, and then we fit it. We got two models. So we had the linear predictor model, and then we can compare that one to our two binary outcome models. So I guess 3 models. And these gave us coefficients. The first thing you'll notice is that the coefficients are not comparable directly. So this has a very different intercept than the logit, and the logit has a very different intercept than the probit. So the first thing to notice here is that the coefficients are very different depending on the model. And this is the first word of caution, right? The coefficients are going to give us very similar predictions between the logit and the probit, but the coefficients themselves are not comparable. One of them is estimating a log odds ratio, and the other is estimating using a normal CDF. So the coefficients themselves are just different domains. But when we plot the models themselves against the data, you can see a couple of things. The first is that the vertical axis for logit and probit, we don't actually cross the 1 or the 0. So we have this nice sort of curvature to the models themselves. We kind of squish the line into the 0 and 1 on the vertical axis. This is by construction. This is desirable. This is how it should be. There's no real way of getting around this problem, or getting around this this structure to the binary outcome model. It's like for very extreme values on either side, we should be very close to 0 or 1. But then in the middle, we sort of have to transition between 1 into 0. And there's no way around this. This has to be true for our model. And you can see it matches actually a lot of the empirical regularity of our model. Of our data. The other thing you'll notice is that the binary outcome models are just better predictors. They match more of the data than the linear model, which is, I think, to be expected. If we're doing our job correctly, we've picked the right model to match the data generating process. And then all we have to do is estimate the parameters. Okay, so, and then the third thing maybe is that logit and probit are very similar. Okay, so that's a bit of review. The reason logit and probit look similar is because the logistic PDF and the normal PDF are nearly identical. We talked about why these things kind of look similar, and sort of how they're different. The normal PDF is the result of the central limit theorem. Like, there are other ways you can derive the normal PDF, but the main idea with the normal PDF, the reason we love it and you see it everywhere in the world, from really anything that involves repeated observations and then sort of a sample average. This is from the central limit theorem. So like lots and lots of things are the result of averaging. Just for example, measuring the quantity of rain in a bunch of locations, the distribution of rain across geography follows an approximately normal distribution, because measuring rain is the result of like thousands and thousands of raindrops. So there's lots, like you can think of measuring rain as a very large sample size. So then the distribution of rain is going to look normal. So it's not just in the way we construct statistics, but when sort of nature does averaging on its own, that's where we see the normal distribution show up. So there's like behind the scenes, like we don't have to be doing the central limit theorem to see it appear in real life. So that's the central limit theorem and the normal distribution. The logistic is also really nice for a lot of reasons, but it's not the result of the central limit theorem, but it looks very similar to the normal. Okay, so that was from last time. In general, like you're not gonna have to worry about which one you pick. Sometimes thinking in log odds is nice, so you could pick the logistic there, and sometimes your data will be sort of a central limit theorem result, and then in that case you might want to use probit, but the predictions are not going to vary substantially. So what we did is we tried to improve the model fit. So it's like, maybe there's something special about very long field goals beyond the 40-yard line. And so what we did is we included not just distance, but we included a second predictor variable. So in addition to the intercept and the distance, we also included something about something special beyond 40 yards. So that was this model. We had the intercept, we had the distance from the 100-yard line, and then we had the yards over 40. And it looked like this. So it looks like there is something special over 40. Although our p-value is a little bit large, but it looks like there's something going on here. So what I did is I just ran all three of the models with this extra bend in the model beyond 40 yards. So what you can see here is including an extra bit of information about where we are on the field. We can actually bend the linear model. And I think this looks like a much better predictor. But some words of caution here. First off, we constructed this post hoc. So I plotted the data, and then I used the visual to give us some additional information about where to bend the linear predictor model. So that's one bit of caution here. It's a post hoc construction. And then the other thing is it actually, including that kink in the linear predictor model, linear probability model, it actually makes part of the problem of LPMs worse because we hit 0 on the vertical axis much earlier than we did before. So even between 50 and 60 yards, we hit negative probabilities, which is not a desirable property. But we also see a kink in the binary model, so this is a little kink here. It's actually not that much of a difference once we include this in the binary outcome models, which is interesting. The other thing, I think I mentioned this last time, I wrote my outcome, the main outcome in my dissertation was a binary choice. So it was, did you vote or not? And I used a linear probability model. The reason I was able to do this is because I had lots and lots of covariates. So I used many, many predictors in my model, which turned a simple yes or no question into something that was, it's like it got closer to sort of the middle of the distribution. So it pulled everything away from the edges because I had a lot of covariates. So it's not true that you should never use linear probability models to predict binary outcomes, but you just have to think carefully about how to do it. The upside with them is that they are easy to interpret. The downside is that they're wrong. So that's a real trade-off. All right, so then I constructed a table here. I didn't print it out because we have a nice figure, but if you're interested in the table directly, you can have that. So nice. The last thing we did was introduce an indicator for whether the kick is high pressure or not. We talked about the Steelers-Ravens game at the end of last season, and just like how high pressure it was. I will remember that kick the rest of my life, I think. So what we did is we modeled whether it being high pressure or not was important in the model. So we defined it as high pressure if it happened in the last 30 seconds of a close game. So you had to be trailing, so the team had to be behind, but had to be behind by 3 or fewer points. So making the field goal basically would win you, or would mean you didn't lose. So you could either tie or you could win. And it had to be in the last 30 seconds of the game. So this is an amazing thing to test. And what we did here is we included it as another predictor. So we had the intercept, we had the distance from the 100 yard, and then we had whether you were over 40. And then we also had our high pressure. This is the logit. So this is the log odds model. And you can see it's clearly much less likely to go in if the kicker is under pressure. So whether this is like a model of choking, or whether this is something else about the game, like kickers in high pressure situations are asked to do more because they are the last resort. So that might be involved here. We can't really directly tell whether this is well, I guess, yeah, I'd caveat that because we're controlling for the distance from the field goal. But there's something special going on here with high pressure situations. Okay, any questions? So then one of the benefits of doing linear probability models is we can easily interpret the coefficients, where in binary outcome models like logit and probit, it's much harder to interpret the average effects. So what we did is we talked through a way of estimating the average effects in binary outcome models. This was the picture of the marginal effects. So for the linear probability model, it's just constant, right? The model isn't doing anything special by changing how important the predictor variables are at any point on the domain. So in this case, the distance from the field goal, it has a constant effect across the field, where the truth and the binary outcome models actually give us a more complicated story, where the effect changes depending where we are, which is the truth. When we're really close, moving back a little bit doesn't matter so much. When we're sort of marginally close, that does impact your probability of success by a little bit more. There becomes a point where moving back doesn't decrease your probability of success by much because your probability of success is low already. So that's what happens out here, where the linear probability model is just constant. It just gives you an average effect. So what we want from, one of the nice things about using like models like this is it gives us an estimate. But the problem with the binary predictor models is that binary outcome models, is that they're hard to interpret, where the linear probability model is very easy to interpret. So what we did is we talked about a couple of different options for how to communicate our results. The first one was the marginal effect at the means. So this was, we're just going to plug in the average of our data. So we take the average distance and we plug that into the model, and then we ask it what it produces. So the picture would be, let's just figure out which one of these distances is about average, which turned out to be something like 25. And we plug that into the model, and then we get the slope at that point. This is one way of communicating our results, the MEM. So we take the slope at our mean, so x bar, and then we plug that in. I'm not doing the math here, but this is, so p prime evaluated at x bar times 1 minus p prime evaluated at x bar. This is the average of the this is the slope of the model at x bar. And then the binary variable situation, we can't use a derivative. So what we're doing is just looking at a small change. So we look at x equals 1 and x equals 0, and then we just take the difference. So that's the MEM, and we found that the average at the mean distance was around 20, and then the predicted probability at that distance was right around 90%. So what we did is we just took the marginal effects at the means at these points. So we just plugged in the averages. So the average, the slope at the average for the main variable was this thing. So this told us how much an extra yard would impact the probability of success at the average x value, which is very similar, if you remember, to the estimate for the linear probability model, which was here. So negative 0.0117 versus negative 0.01. So very similar estimates, but I think theoretically the MEM is not quite what we want because it's not giving us sort of the full distribution. So what we did instead, and I think this was the last thing we did, was talk about the average marginal effects, which is the one we use more of. So we want to look at not just the average x value, but we're going to look at all of the x values in our data, so the actual draws themselves, and then plot the average of the slopes at each one of these x values. So we're going to take the average over this thing. So this is the same function as this. It's just, instead of evaluating at one point, which is the average, we're going to take the average outside of that function. So we're going to say, we're going to plot, we're going to get the average at each one of the x values evaluated, getting the slope at that point. Okay, so that's the whole thing. This turns out to be a little bit closer to the linear probability model, and still is, it has all the nice properties that we would like. The model itself does the prediction correctly, at least like the structure of it makes more sense than the linear probability model, and we can communicate an average. And I think that the average marginal effect is sort of the same kind of concept as the slope in the linear probability model, right? Like the beta in OLS is just the average effect. And what we're doing here is communicating an average effect. So the concepts are very similar. So this is really nice. I think maybe, was this the last thing we did? We compared the logit to the probit, and you can see they're very similar. We did talk about the latent variable framework. So this was, and we're going to spend much more time on this in the multinomial. But this is a way of conceptualizing what binary outcome models are doing. Essentially, all we're doing is constructing a composite score. So it's we're just trying to, before we pick whether it's 1 or 0, we just order things. So the horizontal axis is just the vertical axis is going to be y, and then we just pick whether the variable, y star, and then we pick whether the latent variable turns into a 1 or a 0 based on whether it's greater than 0 or not. So I want to spend some more time on this in a second, but the last thing I want to do is talk about recovering parameters, which is not something we talked about last class. Or if we did, we just mentioned it without any deep insight. But we're going to come back to the latent variable framework because it's going to set up our multinomial model. Okay, so with the NFL example, we can think of well, we'll talk about this later. Simulation is useful not just for using like estimating things like pi, right? That was the big example we used. When I think about Monte Carlo simulation, that's the picture I have in my head, is like, I'm going to plot a bunch of data on a square, and then I'm going to use mathematics using the data point to then check whether it's inside the circle or not. But the way that worked is we knew something about either the data generating process or some function about where the data was on the square. What we have here is an estimated model. So what we're going to do, we can use Monte Carlo to actually construct parameter estimates. Let's actually jump this. This is estimating the coefficients, and what this is doing is giving us an estimate and comparing it to the truth for the coefficients themselves. But the big thing Monte Carlo simulation can do for us in the context of binary outcome models, and actually really any model we like, is allow us to easily and without doing like Fisher information matrices behind the scenes, we can actually construct confidence intervals and standard errors using simulation methods. This is used common enough that I just want to spend like 15 to 20 minutes talking about what Bootstrap is. The basic idea with Bootstrap is that instead of using the Fisher information matrix, which uses sort of the, like, you spend some time doing this, it uses information about the function itself. What we can do instead is actually just perform a gazillion resamples. And then we can use the variability across each of these resamples to estimate the variability in the data itself. When I first saw this, I thought this was really weird, that we could do this. The first key thing to note about Bootstrap is we're going to perform resamples. So I have my observations. Let's say my observations are roughly 10,000, which is what happened. That was the sample size we were working with before. I'm going to perform resamples. I'm going to draw one observation from my data set with replacement. This is the key idea that makes all of this work. Bootstrap requires resampling with replacement. So I'm going to pull one observation out of my data set that I have observations from the real world. So this is coming from the underlying distribution. I'm going to resample, observe my xi. I'm going to write down that xi, and then I'm going to put the data, the observation back in my data set, shake it all up, and then resample again. So I can, in my Bootstrap, have the same observation appear more than once. In fact, I'm almost guaranteed that it will. So this is the first idea. We're resampling the data with replacement. Then every time we're going to go through and collect a sample size of the same size as our data, we're going to refit the model. So if the original sample size is 1,000, I'm going to resample with replacement from that 1,000 till I have a sample size of 1,000, which is not going to be the identical same distribution as the original data. I'm then going to fit the model using the resampled data, and then I'm going to do this a bunch of times. Each time I resample, I'm going to get a different data set, which is coming from the underlying distribution if my sample size is large enough. And then I'm going to get the distribution of parameter estimates across a bunch of observations, across a bunch of resamples. Everyone on board with how we're doing this?
Can you give just like a brief reminder of like what you mean by replacement with resampling like that? Like
Yeah.
putting back in.
So I have a bunch of my observations. So I went out and collected 1,000 observations in a big pile. And this is like, these are drawn from the real world, the underlying distribution. So these are the real deal. What I'm doing is I'm grabbing one, I'm observing what it says. I'm writing that down on a separate piece of paper. I'm putting that back in, shaking it up, and then drawing again. So that's the resampling with replacement.
Until you get 1,000 on this sheet of paper that you're writing.
So then this sheet of paper contains the same length, the same sample size as my original.
Okay, that makes sense.
Yeah, good. Any other questions here? So this is really powerful. The reason is we can perform all of the kind of Monte Carlo kinds of tests on parameter estimates without having to do anything analytically. And it doesn't really require a lot of extra assumptions. This is very robust. And you can think about why. Every time we draw from the underlying distribution, so long as our data set sort of covers the distribution, like as long as our sample is large enough, it's going to, we're effectively drawing from the underlying distribution when we sample from our data. Let me try to like put some stuff on the board to make this incredibly clear. So we have the underlying data generating process. So our data generating process, which gives us our data, which is just a list of x1, x2, x3, all the way down to xn. This is drawn from some underlying distribution, which is what we care about, right? This is the data generating process, which we have questions about. So all of our questions are about the data generating process. We get this. We could just make direct estimates of our model based on our data. But what we want, in addition to the parameter estimates themselves, is some measure of how the estimates vary. And that's what inference is doing. So this is, inference. Inference requires understanding how the parameter estimates change when we resample. The core idea in Bootstrap is that we can just resample from this thing. So we can resample to get a data set that's equally long. So this could be, x1000 or 100,001, say 101, x3, and so on, all the way down to whatever it is. Like I'm just drawing random numbers here. So like 506. As long as these two have the same length, and as long as this is a good, like this sort of covers the data generating process well, as long as our sample size is large enough, then this is going to give us parameter estimates that will be centered on the truth. So if this is our beta, then it's going to give us parameter estimates that are centered on the truth. So this is, let's call this beta truth. This is the entire idea. So we're just resampling from our data. And the reason this resample is not identical to our original data is because we're resampling with replacement. So our resample is not going to be identical to our data, which gives us this variability. So this is the variability due to resample with replacement. Okay, any questions here? That's the forest. Now let's do the trees. So these are just some functions. This is the bootstrap function that I wrote. I'm just going to give it the data set, statistics that I'm interested in, and then this is just, by default, I'm going to sample 1,000 resamples. This is just for reproducibility if we want a random seed. So all this is doing is just running through a loop. I'm keeping a list of the estimates. This is the length of the data, so this is saying how many observations I need to resample with selection. And then I'm going to do this for each time I've listed in the number of bootstraps. So this is just here. This is just a function in Python that allows me to quickly get a sample size. So this is just a bunch of replacements. These are the indexes. And then I'm using those indexes to select the new sample. So this is just essentially code for doing resampling with replacement. And then this is just appending to the estimate list the statistics. So this is going to take in sort of a function. So this is just returning a function that generates or returns the estimates in the estimate list, and then the entire bootstrap function just returns the estimates, so the list of the estimates as an array. And then this is for the standard errors. So this is the standard deviation of the estimates is the standard error. So remember, standard. The idea with the standard deviation is that it's the distribution, the standard deviation of the estimates themselves. And typically, the way we get the standard error is through math. So with OLS, we were saying the standard error, the variability of our beta hat, is the standard deviation of the data divided by the square root of n. But here we don't have to do that math, and in fact, analytically, it's very challenging when we're dealing with nonlinear models. So what we do instead is with Bootstrap, we can just measure it. We run a bunch of resamples, and then we measure the spread of this thing, because we can see 1,000 different model fits. So we can actually just observe the variability directly. And then we can get confidence intervals. Okay. So let's see. We talked about the car ownership model a little bit. I think, when did we talk about car ownership? Do you remember this? I was trying to predict how many cars a family had using income and a few other things. Maybe that's maybe this is the first. I might be thinking of my prep for the class and didn't actually talk about it. So this is a new data set, I guess. So what we're doing is just we're going to generate some data. So this is we're going to try to estimate whether a family has a car and how many cars they have using a couple of covariates. So we have just Bernoulli draws. So this is some, let's see. Where is this coming from? Oh, we skipped it. So this is the parameter recovery, which we're skipping right now. But this is, if you want to go back and look at that, I'm essentially just verifying that our procedures generate the truth. So this is just using a generated data set. So this is x1. And then we're generating x2 as a random normal distribution, and then we're just setting up a little model here. This is, we have whether you own multiple cars, so this is binary outcome, so yes or no. We have whether you're married, so this is also yes or no, 0 or 1. And then we also have the household income. And I think we did something similar to this for the number of children. But we're saying that whether you're married or not is related to the household income. And then we're just going to take the log income. I fit the model for the original, and you can just check that the estimates are similar. So here, what we're doing is using that data set, but then we're performing bootstrap on it for this model. So remember the forest as we go through the trees. What we're doing is resampling to get many, many different data sets that are coming from the same underlying data generating process. And the reason we can get many data sets is because we're resampling with replacement. And then all I'm doing is using that data set. I then have a logit function. So I'm just, I'm giving it some data. I'm calling that df boot. So this is the data set internally. So whatever data set I give it, it's going to build a statistical model. This is, I think, unnecessarily complicated. Basically, all this is doing is just estimating this as a model. So this is the logit. I'm trying to predict whether you own multiple cars. I'm using the married binary indicator variable and then log income as the two predictors. So we're going to get a beta 1 and a beta 2 in the logit model, including a full model. And then, so I have this logit coefs, and then you'll remember I had this bootstrap function which ran like 1,000 resamples and then generated coefficients using whatever function we gave it. So you remember that was the statistic. So I'm just sending into the function another function itself. And then it's going to return a bunch of bootstrap estimates based on the model that I'm running. So what we get with boot estimates is the coefficients coming from the logit model, but resampled like 1,000 times. And we're saying that it successfully converged in every one of the runs. So this is an incredibly powerful thing to be able to do. Like, the theory works. Like, you can see we're basically just resampling from the underlying distribution so long as our original data sort of covers the original distribution well. And we don't have to do any analytical real work to get the standard errors. And we can use this for inference. So we can make claims about whether our parameter values are different from whatever value we're interested in testing, which in general is usually going to be 0. Our default null hypothesis when we're performing inference is that our parameter value is 0. Okay, so this is nice. And what we're going to do here is just compare the asymptotics. So inside the logit model, we can actually get the standard errors. So this is the asymptotic standard errors. So using the inverse of the Fisher information matrix and that whole procedure, which relies on the analytical solution. So that's what these analytical standard errors are. I've also constructed the bootstrap standard errors. So this is just using bootstrap standard errors from, so this is the boot estimates, and then I'm getting the standard errors from that. So we have the boot SE and then the asymptotic SE, and then what I'm doing here is just comparing them. So the standard error asymptotically looks like this. The bootstrap standard error looks like this. And you can see that they're very, very close across each one of the 3 coefficients: the intercept, the married, and then log income. You can see the ratio of these things is always very close to 1. It's not 1. And that's because there's going to be some sampling variation. So the theoretical and the bootstrap are going to just not be identical, simply because we're doing something random here. but they're very, very close. And you can think back to like how precise these things are. You remember it took us a lot of work. Like our sample size had to be very, very large when we were estimating the digits of pi. Like we had to take very large samples for Monte Carlo to be incredibly precise. And that's part of the mismatch between these things. But what's amazing about this is that we don't have to rely on the theoretical structure to get our standard errors. It turns out with like the standard package like Probit and Logit, those models are just going to give you the standard errors using the Fisher information matrix. But if you were estimating a maximum likelihood from scratch, like we will do later, Bootstrap is just amazing at giving us the standard errors. So what I'm hoping you leave this class with is not just the tools to actually do the thing, but the ability to like construct from scratch your own models. And Bootstrap allows you to construct standard errors very, very generally, which I think is an incredibly useful skill. Even if it's never something you'll do, just knowing that that's available can give you the confidence to sort of do the harder things, even if you actually never use it. Okay, nice. Any questions here? So this is the theory for Bootstrap. It is incredibly robust, and it doesn't require knowing anything about the parametric form or the functional form. This is just a picture of the distributions. So this is, here I've just plotted, remember we ran like 1,000 resamples, and what I've done here is just plotted the distribution of the parameters. So this is the intercept parameter. The point estimate is here, so right in the middle. And then the true value is here. And what you can see is we have the same sort of kind of conclusion as we do with asymptotic results. Our point estimate, the estimate we make from the sample. So our point estimate is coming from a single sample that we observe. Our point estimate is not, our point estimate will be close to the truth. So our point estimate and our true parameter, which we know because this is constructed data, these things will be pretty close. Right, that's coming from the central limit theorem. We know they'll be pretty close to each other. Or the law of large numbers will get us close. And what you can see, in addition to that, is that the sampling distribution around is centered on the point estimate. So we have a point estimate which comes from this. Every time we resample, it's sort of like we're deviating from our point estimate by a little bit. So the sampling distribution of the Bootstrap resamples is centered on our point estimate and not the truth. We're never going to observe this. This is standard hypothesis testing ideas, right? Like, we're never going to observe the truth. What we can observe is our point estimate, and then however we choose to derive the sampling distribution, the distribution of our betas. However we choose to do it, either asymptotically or with Bootstrap, that distribution we can center on our sampling distribution, or our point estimate. And that allows us to make probability claims about where the truth is. And in all of these cases, if you were to construct like a confidence interval, whatever that confidence interval is, it would contain the truth that amount of the time. Any questions here? So the only fundamental difference with what you've seen before is that we're constructing the sampling distribution by Bootstrap. And it's remarkably consistent. Okay, so nice, here are some confidence intervals, and you can see what they look like. And then we can also, in addition to standard errors, we can construct the really any parameter estimate we like. So here, I'm just going to go through and construct marginal effects, average marginal effects. So there's not a lot of like deep insight here. It's just we're going to resample from our field goal data and then go through, run a bunch of, you can see how long this is taking. We're going to bootstrap 1,000 from our field goal data and get the average statistic. So that looks like this. So we can get sampling distributions of our average effects. So not only can we use Bootstrap for standard errors, but we can also get the point estimate, and then this the Bootstrap standard error of the average marginal effect. So think of this as just an incredibly flexible way of getting sampling variation on whatever parameter we're trying to estimate. So this is giving us the spread of average marginal effects, specific for the high pressure situations. Okay, so there's not a lot of deep insight here. It's just we're estimating the distribution of average marginal effects when we resample. And I think this is not like, if I were to try to do this asymptotically, I would not know how to do this, I think. Maybe I'd figure it out sitting in my office for a while, but this is a hard thing to do. And here we can check against 0. We could do this very easily, actually, in OLS. We just check the beta, like the beta 0 is the effect. So we check the beta 0 against, the beta against 0. But here, because we're checking the average of the slopes at all of the data points and checking whether that average is 0, like, I don't know how to do that. So we can just simulate it with Monte Carlo. Okay, so that's awfully nice. Why don't we take a break here? This is just some model comparison, but this is just to say the two models are very close, probate and logit. Okay, any questions here? You'll want to take a break? Obviously. Sorry, that was not about you. That was like, obviously we always want to take a break, everyone. Let's see, are we at 7 minutes today, plus the 4 I owe you last time, so 11. Do you want to take the 11 minutes all right now? It's a little too excited for an 11-minute break. Yeah, let's take 11 minutes. We'll come back together and talk about, I want to give you the basic idea for ordered models. We're not going to do it in detail. And then I want to talk about the checkpoints. And we'll talk through those until we're done with that. Okay, 11 minutes. Let's see, 10:27.
only you in here now. Everybody left.
I never really leave during the breaks, but probably good for me to do that.
Yeah.
Yeah. Oh, I'm fine. How was your weekend?
Good. Okay, who is in here so like the store is not functional?
They're so weird. Honestly, just this whole room. Nothing really works right.
Yeah, that's a good point. Yeah.
Ugh. Oh, sorry, you're good.
Canceled all car classes for like 2 or 3 days.
It's crazy if we just told them that.
I know.
I know my friends that have a car, they don't have
Yeah. Yeah.
Usually it's the draft of the actual day, but it's
24th.
I hope they do.
I know. But I was like, I feel like there's no way that it does it. They don't cancel
Yeah.
Friday. And we would just have remote class anyway.
Yeah.
I bet they'll make it remote optional. Yes.
Tim, do we have anything to do for regular class? Yeah, tomorrow. The spatial data for the lesson. I just had a subject I really did. Yeah. He was like, he wants to just have, it's open-ended, you just need to fine-tune like spatial data things. I'm so glad you're
Me too.
I need to do that as well. And then I guess I need to do reviews on it. Is it gonna take a while?
I don't think so.
Also, like, last time we like did that, every week. But maybe this one you might, because we're all doing different stuff. Yeah.
I haven't tried.
That's exciting.
No. I haven't worked out in so long. I went on a 2-mile run yesterday and I was like, oh, it's gonna be real bad.
I'm still impressed.
It's so bad. I literally had to like call them and change my registration to be the short distance instead of the long distance because I was not capable of doing the long distance.
Oh, I couldn't even do the short, so that's exciting.
I feel like you could.
No.
I feel like anyone could do it, like if you have no time limit.
How long is it?
It's a half-mile swim and then a 12.5-mile bike ride and then
Okay.
like it's really not bad.
Yeah, I can do the biking one, but I don't know.
The swim's hard because it's open water.
Yeah, that's the part where this is a triathlon.
Mm-hmm.
Where is it?
Virginia.
Oh.
Yeah. It's in Bumpus, Virginia.
Oh.
And it's called the Bumpus and Bumpus Triathlon.
I have a couple friends who like race triathlons, but they don't like traveling for them, so they do very few of them.
That's so fair because I'm like nervous about driving my bike on a shaky bike rack for 5 hours.
Yeah, that's fair. Who works on tri-bike? Like, where do you take your bike to work at?
I don't even own my own bike. I have an uncle that lives in Fox Chapel who's super into cycling. So
Okay.
I just, every time I have a triathlon, I borrow a bike from him and I give it back to him.
Okay, that makes sense.
Yeah.
That makes sense. My partner's a bike mechanic,
Mhm.
and generally, it's funny because like people enjoy racing triathlons, but bike mechanics hate working on tri bikes.
Really?
So it's like I know a couple people who also like have a hard time. They're just like kind of weird compared to a lot of other like, racing bikes.
That's so fair. I literally, for this weekend, I'm so just like not even trying that I'm bringing a mountain bike because I'm like, I'm just gonna take a nice little stroll, basically. I'll come last, and that's okay. Really? I get like really nervous bike riding. Like I'm like not good with it. I think it's because I probably only train on stationary bikes and then I am thrown onto a bike on race day.
Is the like bike terrain is it usually like roads?
Yeah.
Is it, okay. It's
Which is
not
why
trails
it's
and
silly
stuff.
that I'm using a mountain bike, but it's the most comfortable of all
Whatever.
these.
Yeah, who cares? Fine.
That's usually the effect I have at parties. I walk in and everyone stops talking. It's a tough life, you know.
Sure is.
That's why I usually leave early.
Mm-hmm. I feel so off now though. Everyone's like, I'm like driving like a car full of 18-year-olds to Virginia. I'm like, okay. This is silly. And they're also so intensely because I like don't even go to practice anymore. And there'll be like our like 19-year-old vice president will be like, I really expect everyone to be at swim practice tonight. And I'm like, okay, can we take a breath? Because I'm not going. Like, I'm sorry. I don't want to go.
Where do they practice?
At the rec center. But then I go and they're like telling me what to do and stuff, and I'm like, I think I'm gonna swim on my own. I'm sorry. Like, I can't do it. If we had a coach, that would be different. But I'm like,
Yeah.
I don't know. I'm gonna do my own workout. Maybe I'm a bad team player.
Well, isn't it? Do you score collectively?
No, that's why I'm like, why
Yeah.
do you know what I do?
Right.
I'm like, oh my god. And it's also like, most of these triathlons have no one in our age groups anyway. And so like, I did one in October, and I actually didn't try whatsoever. I like walked the majority of the run section, and I won the run in my age group.
Okay.
Because, like, and it was like a 35-minute 5K, and I won it because there's like
Solid.
no one that does these our age. So
That is true. I do feel like everyone I know who's gotten into triathlons is like post age 40.
Yeah.
That
Yeah.
was the thing
Yeah.
that they started doing.
No,
it's-
totally.
it's not
Yeah.
weird. If you want to go get a medal, do a triathlon at 22. It's fun.
So it's a 5K run?
Yeah, I mean, normally we do like the distance, which is
Yeah.
like a mile swim and then a 50K bike and then a
Yeah.
10K run.
Okay.
But I'm doing the half sprint distance this time, which
Yeah.
is half of all of those because I'm like.
That's fun.
Yeah. Yeah. I didn't do anything enough.
Yeah, I've never done a triathlon.
You've never done one?
No.
I feel like that would be right up your alley.
I don't swim enough.
Hmm.
That's the. Yeah, I used to do a lot of swimming and
They have
Kinda
some
stopped.
triathlons that have a kayak leg instead of a.
Okay.
You should do that.
I do a lot of rowing, so if it was like rowing instead of swimming, maybe I'd do that.
Yeah, fair.
I'm doing a 17-mile run later today.
Wow, for the
It's
marathon?
yeah, it's the second to last long run.
Are you going to try to qualify for Boston?
No, not this time.
Okay.
I'm not that fast.
Fair enough.
This is actually my first marathon, and it's
Oh.
Pittsburgh, so it
Hard.
yeah, lots of hills.
Nice.
So yeah, I'm signing up for Philly, which will be a lot faster. And yeah, if the training goes well, I think I can get close, but I probably won't qualify for a while,
Yeah, fair. It's hard.
probably a year.
I feel like I could like someday get right at the qualifying time, but
Yeah.
never actually make the lottery or whatever. Because like they
Yeah.
still only a certain amount of people.
That's right. Yeah, if you're close to the cutoff,
Yeah, you can
then
still
it's a
not
lottery.
do it.
I think if you're like deep into the qualifying
Yeah,
times,
then
then
you
you
definitely
definitely make it.
yeah.
But I have a friend who has done almost all of the majors.
Really?
Yeah, she ran, I think, yeah, Boston. She did Chicago, Berlin, and I think she did London, which is so cool, so inspiring.
My boyfriend's mom has done a marathon in all 50 states.
Oh my goodness, that's
Isn't that
wild.
correct?
You've been in Alaska and Hawaii?
Yeah.
That's like crazy.
She's insane.
Where in Alaska? Do you
I
know?
have no idea.
Okay.
Yeah, she's been doing it since long before I've known her, so it's
Mhm.
like been her whole adult life. She's been doing it.
Wow,
Mhm.
that's amazing.
Yeah.
That's so cool.
Yeah.
Yeah, I want to. One of my life goals is to run to be qualified for Boston when I'm like in my 70s.
That'd be
Like
so
to
cool.
run that.
The bar gets pretty low.
Yeah.
for adults, so
Yeah.
that's your chance.
I know. I just crossed over from like the most competitive. It's like I think you have to be like. It's like 255 to 3. Is like the highest, the fastest qualifying
Right.
category. So now I think it's like I'm now in like 305.
Wow.
So
moving up in the world.
yeah, maybe a little more reasonable. Speaking of reasonable, can I show you something interesting? You know how like, I mean, you're all economists. You love economic theory. You know this idea. I think we talked about this briefly last time. Like, we can never observe utility. Like, if I ask you how many utils we would generate if I let class out early, what number would you give me? It's like you have no idea. Utils are meaningless. We can model, but the idea is like you can compare utils across different things, right? It doesn't matter what the actual like level is. The idea with utility is that we pick the thing with the highest utility, and it doesn't matter what the baseline numbers are. We sort of think about these discrete outcome models in a similar way. So we talked about the latent variable framework a little bit last time, we can do this, I think like in the binary case, the latent variable framework is not that useful. But it becomes useful when we start talking about ordered outcomes, which is what we're about to transition to. Just briefly for like 20 to 30 minutes here, and then we're going to talk about checkpoints. So the basic idea, like we talked about last time, is there's this underlying y star, which we are not going to observe. The only, like the main thing with y star is that we just want our values to be ordered correctly, or like as correctly as possible, so that when we come in, we can slice it into two groups. So all we need for y star is that the order matches, or like is as good as it can be. So we want things that are more likely to be 1 in our data. So we're trying to predict a data set that's zeros and ones. I don't know if I listed that anywhere here. So like with kick quality, we want to think about kick quality using the covariates. So like distance and high pressure and all of these things. And we want the probability of success to be related to y star. So if it's more likely to succeed, we want it to be on the upper end, and if it's less likely to succeed, we want it to be on the lower end. And all that this is doing, this y star is doing, is just ordering things. So, I mean, I was trying to think through like intuitive examples of this, but like, it's sort of true at the master's level, but like, especially for very large intro classes, for me, what I try to do with my grades is just order people based on how much I think they get the material. And then what I do is I just split them by grade. So it's, as long as my numbers are correct, or like, as long as my numbers are kind of ordering people according to how much I think they understand, then I can split the grades however seems fair. This is not to have a good discussion about like what fairness means and all of this stuff. I've books and books on my desk about how to. That's a separate conversation. But the idea is that we want the underlying latent variable, which in my analogy is your grade, or the point number for your grade. And then we split that number based on breaks, wherever we choose to break things. So like an A versus a B is at 90. So we want to split in that way. But we want the number itself to rank people. So that's what the Y star is doing. And then Y is just figuring out how we do the breaking. With a binary outcome model, this is very uninteresting. All we're doing is breaking at 0. So we're just setting up our model to do the ordering and then splitting at some 0 point. We can do this at 0 because we have one intercept term. So we can just move it up or down, and then it really doesn't matter where we break it because we can just pick our intercept. So I'm just going to pick a 0 because it's natural. It's like a nice place to split.
So when
Yeah.
you're saying that it's unobserved in regards to like the grades example, does that
Yeah.
just mean because you don't know what their actual final grade is going to be yet because you're curving it, or?
It's more like I don't observe their true, my big undergraduate class, I don't actually observe their true understanding of the material.
Oh.
What I'm doing is I just have like their homework scores, their exam scores, their in-class exercises. And I'm using all of that to try to predict whether they understand or not. And I can't see it, but what I'm trying to do is order them based on this information, whether they actually, I'm trying to order them according to their understanding, even though I don't see it. So then, the analogy kind of breaks down because here we actually do observe whether they get it or not. But we don't observe their number, we just observe their whether they get it according to different levels. So that's the basic idea. This is the forest. And I think if you get this, the rest of what we're about to do is going to make a lot of sense. So we don't observe y star directly, but what we're trying to do with y star is order it so that we can break according to some breakpoints, some thresholds. Binary is uninteresting for this example because it's very simple. The way we do the breaking is we observe what percentage of the, in my example, what percentage of the class gets it. And so they're assigned 1, and what percentage of the class doesn't get it, and they're assigned 0. And then what I'm going to do is, using my ordering, is pick a breakpoint that assigns some percentage of the class A's, and that percentage of the class getting A's is going to be the same percentage as I know get the material. But we don't know whether it's the same people who are getting A's that understand the material. We're using y star, and then we're picking the CDF so that we're picking the breakpoint so that the same percentage of the data gets an A. But we don't know whether the people getting the A's are actually the people who understand. Okay, any questions here? That's the intuition for what we're about to do with multinomials. It's just, instead of one breakpoint, we're going to have many breakpoints. But behind the scenes, we're doing this sort of blind ordering, or like imperfect ordering. And then we're splitting the data in this way so that we use the CDFs. We're going to match the proportion, getting each of the outcomes according to the observed proportions. And that's where the imperfection shows up. That's sort of our model misspecification, or our model error. All right, so that's the big idea. So let's turn to ordered models, and I just want to talk through some of the basics here, and then maybe we'll get through checkpoint 1. So that's the basic idea. Using this latent variable framework, we have this unobserved thing, y star, and we can see in the binary case how many are getting y equal 1 and how many are getting 0. And then we just break based on the CDFs. And it turns out it doesn't really matter if we're using logit or probit in general. But often we have data that's more than binary. So there are more than 2 outcomes, and it's still ordered. So something like a Likert scale. So it's like I strongly disagree, I disagree, I'm neutral, I agree, I strongly agree. Credit ratings are kind of the same idea. And then if you look in the census, you can see educational attainment in the population. So like the highest degree that you've earned, which for you in about 3 weeks, what's it, 3 weeks? 2.5. 2.5, yeah, depending how you round it, is can be master's level. Not going to congratulate you yet, but I will. So these are the kinds of things we're going to try to model. There's more information with a Likert scale than there is with a binary scale. So do you agree? Do you disagree? A Likert scale obviously has more variability. And what we're trying to do is build a model that captures that. And the way we're going to do it is identical to the latent variable framework in the binary outcome case. We're going to try to use our predictors, our betas, our x's multiplied by our betas, as a linear model. We then send that into a link function, and then we're going to try to match the categories. So yeah, grades actually is a good example here. I can't see if someone actually understands the material, but I can see their, so I don't actually have the Ys, but I do have the predictors. And what I try to do is then just rank everyone according to how well I think they understand the material, and then I use some sort of breaks to create categories. So that's what we're doing. So all we're doing today is talking about the high-level stuff, and then we'll get into the weeds next time. But this is a data set we'll work with. So I have 4 different options here. So did someone buy a thing? Did they buy the basic one? Did they upgrade? And did they get the deluxe? So with the latent variable framework, we're just going to set up this thing. We're not going to see Y star, but we're going to try to construct it. And then we're going to use thresholds to break into categories. So in this case, this is a simple extension of, this looks fancy, but this is really just a basic extension of the binary outcome case. In the binary outcome model, our latent variable framework, we were just breaking based on whether it was greater than or less than 0. But here, we're replacing 0 with a bunch of, why do we do this to ourselves? What's this called? I guess we could check the latex. It's been a while since I've, look, zeta. Okay, so zeta. So we're, instead of 0, we're using different zeta thresholds. Maybe we could use 0 in subscript 0. What a horrible notation. Latex would allow us to do it though. So this is the basic idea. And then the core idea is that we're going to try to minimize how wrong this thing is, the Y star. And the way we measure how wrong it is based on whether the data gets put in the right category. Okay. We don't have any control over, let me say it this way. The main control we have is over the betas. Betas change the ordering. Then the zetas are really just placed so that the probability in our model, so the mass associated with each one of the categories matches the mass that we see. So the number of observations that fall into the deluxe category in our data tells us where to put the zeta 3. So we put the zeta 3 so that our model predicts the same number of observations in deluxe as in the data. Is that clear? I did not get a yes.
Can you say that one more time?
So our model is going to be imperfect with how the ordering happens. And that's going to be, like, every model is wrong in some way. But what our model is doing is picking, after we've done this, our model is going to pick the zeta so that the probability of being in deluxe, so that the number of observations that our predictions would put in deluxe is the same number as the number of observations we see in deluxe. Does that work better? Okay. But the predictions can be wrong. It's just we need the number of predictions in deluxe to be the same number as in the data. Okay, and that's what this thing is saying. Just with sort of fancier notation here. This is just the CDF of one group minus the CDF of the one before it. Okay, so that's the high level, and this is kind of a picture. So we don't, we're going to pick the scale. We don't really care where the scale is centered because we can move the zetas. So we can move the zetas, and just like with the utility, it doesn't matter what the actual numbers are as long as we pick the cutoffs. So I switch from choosing option A to option B when the value of option B grows to be greater than the value of option A. So that's what this is doing. Okay, and then there's a whole lot more here. We can shift these things around, and the shifting is what allows us to pinpoint. It allows us to give the right probability mass to each one of these categories. So you can see, like, we're just going to pick the zetas and the underlying y star so that the probabilities fall into the right categories. Any questions? I see some confusion. But this is the high level. Then behind the scenes, we're going to use maximum likelihood estimation to give us the underlying model. This is not a GLM. So that's what we're going to do next class. I thought it would be most helpful as we make this transition out of GLMs into some of the more complicated models of the semester to just take a breath. And what I want to do is go back through some of the checkpoints. We just, I think some of you are still submitting checkpoint 3, but we've submitted checkpoints 1 and 2 already. So what I want to do is just talk through some of the solutions. You put a lot of time into this. I think how long are these taking you?
A few hours.
2?
Yeah, like a few hours.
Can I get a raise of hands so how many for 2 hours? How many for 3?
Between us two. Yeah.
2 and 3? Okay. Anyone over 3 hours? And this is true for both of them? Or all 3, I guess, if you finish the third?
Third was a bit longer.
I think third was longest?
I think,
At
the,
least for me.
Yeah.
I think the first one took me a little longer, just like getting in. Like the second one felt like it was faster, just because I understood the format a little more too.
Yeah, okay. That's about right. I think if it's longer than 4 hours, then I've made it too hard. And if it's less than 2 hours, then I've made it too easy. So if it's like 2 to 3, that's, I think, right on. What I want to do is just go through these and talk through some of the solutions. I think you don't have to get all of them perfect. Like, the way I'm assessing you all is just, do you seem to understand the core ideas? There's so many trees in this forest. I teach this class, and I don't even remember all the details. Like, part of the world we live in is using reference material. I think getting the landscape, understanding how ideas fit together, that's the skill in any world we will ever live in. That will be an incredibly useful thing for you to be able to do. And to be able to read code and understand how to make changes to code and how to use code to do the kinds of things you would want. So that's what these things are intended for. So I just want to walk you through the solutions. I think some of you have definitely walked through these solutions, but I think just a structured guide walking through them would be instructive. Okay, so the first question you saw was, I think, one of the most challenging, which was how do you take asymmetric numerical derivative. In a lot of ways, this is a contrived example. This is contrived to get you to think about sort of the higher level intuition about numerical derivatives. So I gave you 3 numbers. So we have this one. So this is, f evaluated at x plus 3 epsilon, evaluated at x, and then evaluated at x minus 2 epsilon. And then the question was, what are the 3 weights, alpha 1, alpha 2, and alpha 3? And I gave you the flexibility to not fully answer this one. I think some of you didn't even turn in full solutions for this, which is a-okay. Just getting some thinking with this question is more than enough. But I want to walk you through, and I think there are also many possible answers here. So I first want to show you my best solution, but then there are other solutions to this. So I think there's a whole range of possible solutions. And I think there might be 3 solutions that are there's one that's best, there are 2 that are second best, and then there's, I think, an infinite number of them that are maybe third best. But I think everyone's going to get full credit on this question if you gave it a solid try. So and I sent out a bit of some guidance for this. But the reason this is challenging is because these are off center. We can't just, the basic idea with a second order the second derivative of x at x is that we apply the first derivative twice. The problem here is that the second derivative is not going to use we have 3 different epsilons, 3 different deltas. So it becomes more challenging. The thing I'm going to do is set up 2 first derivatives for the centered, using the centered approach. So the first derivative is going to be on one side. So what I'm doing here is just setting up. The reason we know we need to use the first derivative differently on both sides is because there's no one symmetric way of doing this. But what I'm going to do is I'm going to use 3 epsilon, so I'm just replacing this thing with 3 epsilon here. And then this is just a first derivative. I should write this in the notes, but this is, I'm evaluating this using the center, what did we call it? The centered first derivative. So this is I'm going to put the position, the value that this is estimating the derivative to be halfway between x plus 3 epsilon minus x. So this is x plus 1.5x. So this is just using the centered approach. We have the delta is just the difference between these 2 values, and then the thing we're estimating is just halfway between them. So standard first derivative approximation, and this is the reason I'm saying this is the best version of this answer is because this is the most the most accurate one. Remember, we talked about the centered approach being the most accurate. So this is the first one. The second one is a different value. So it's we're using the backwards direction, but we're going to use the centered approach. So this is x minus 2 epsilon. So this is evaluating this at x minus, oh, I'm sorry, this should be epsilon. So this is minus epsilon. Okay. So this is centered at x minus epsilon, and this one's centered at this one. Okay, so this is nice. These are two first derivatives we can have using approximation techniques. And then all we're going to do is just do a second derivative. We know the two values, and it actually doesn't matter where the second derivative is evaluated at. It's just, we need the two approximations. So this is going to be like x plus some amount of epsilon. And it doesn't actually matter how far off it is. Like, we don't need that for our answer. So I'm going to leave it blank. In my notes, I don't have these filled in using these numbers, but you can see the distance between these two evaluated points is 2.5 epsilon. So our delta in this case is 2.5 epsilon. So 2.5 epsilon goes on the bottom, and then we have the two approximations on top. This is the definition for the second derivative. We're taking an incremental difference between the values of a particular function, which in this case is f prime. So we're taking a first derivative and applying it using the first derivatives that we approximated to get the second derivative. When we plug everything in, we get this thing. So this is gross, but this is everything we used. So we have these two things defined, we have this thing, and then we just plug them in. And then from there, you can just use algebra to solve for the weights. So we just play everything out, and that gives us a function that is, in terms of everything we know and epsilon. And then we can just solve for the alphas. Any questions here? I think this was pretty challenging. The first time I did this took me quite a while. So if it took you a while, that's great. I know at least a couple people didn't turn anything in for this, and if you didn't, then I saw you in my office and you did a lot of good work on it, so you get full credit.
So the final answer should have epsilon in it like that for the weights?
Yeah, that's right. Yeah.
I think I got less because I did it out by hand first, like I just did out the Taylor expansion to get an idea of what the answer
Oh,
would
yeah,
be,
yeah.
And then
Yep.
I messed around with the coding until I got the same numbers.
So you can solve this with the Taylor expansion. Yeah.
Okay.
This is just my way of doing it using the tools we've worked with.
Right.
So yeah, I guess if you gave me like precise numbers, yeah, I'll look at your process and see. But yeah, I imagine you get full credit.
Okay.
The main idea here is I just want you to think about the process, not just take the functions and plug them in. To think about actually what we're doing with numerical derivatives. Okay, so then you just answer these questions. All right, any questions there, or any other questions I should say? So then question 2 was about root finding. So we have this function. I just coded this up. I also coded up the G prime. I think I gave this to you. So then what we wanted to do was use a solver to find all the roots. So this is, of G. And we're going to look for all of the solutions between -3 and 6. So we're going to try a bunch of starting points and then report them. So this is just some code to do this. I used linspace. So we're going to set a bunch of starting points between -3 and 6. And it's going to be 100 starting points. This is the fsolve. So I'm just going to plug in the function. I'm going to give it an initial starting point x0. And then I'm going to report it as a solution if it converged. So this is a lot of code. I haven't looked through this in a couple of weeks, but what this is effectively doing is checking if it converged, and then is it close? Like, is the evaluated point close to 0? So this is just checking, is it close to 0? So is it actually a root? And then if it's a new one, then we add it to the list. And then what I have here are the different values. So this is the root, the x value, and then I'm getting the evaluated g. And then this is just going through the different g's. And you can see they're all basically zeros. And the reason we need to check a bunch of starting points is because there may be multiple. In fact, there are. We need to basically just cover the entire domain. And then many of these will be duplicates, which will get us, if we start 2 points pretty close to each other and they're both close to a root, they will end up selecting the same root. And so we just wanted to get only the unique ones. Any questions here? All right. So then the next thing to do is to find the global minimum. There are a couple of ways to do this. I think this is the more complicated approach. No, this is fine. So all I'm doing is essentially replacing g with g prime. So I'm checking, to find a minimum, we want to find the places where the slopes are 0, so the optima, and then we also need to check the edges, which I think. No, I'm sorry, this is asking for a global minimum, so we don't need to check the edges. So all this is doing is, it's essentially the same code as finding the roots, except it's applied to g prime instead of g. And then I'm finding the critical points. So this is where g prime is equal to 0, which gives us all of the optima. So then these are all of the optima, and then I evaluated them at g. So instead of evaluating at g prime, because we know that's going to be 0, I'm evaluating at g. So then, you can see this is the smallest one. I guess I did check the endpoints. And what I found are I guess these are, oh yeah, I'm plugging in the endpoints, and then I'm checking the values. So this just gives us the minimums, the global minimum. Of all of these possibilities, we have the optima, which are where the slopes are 0, but then also the endpoints could be minimums, and so we have to check those too. I think the way the question was worded, this isn't exactly clear. I think I would get maybe a little bit confused about whether I need to check the endpoints. Well, I guess global is not asking for just the local. So yeah, this should include the endpoints.
Could you explain why you doubled how many starting points this time?
There's not a good reason. I think I just wrote that.
Okay.
I think you'd find the same solutions if you used 100, probably even 10. Okay, any questions here? Okay, so this is to distinguish global and local. So this is just walking through the second derivative, and then we're just going to check the critical points. So I think you could do this by hand. But this is just me coding up using the second order condition. So just checking the curvature around each of these points. So because the second derivative at the critical point was positive, so then it's, curved upward. So this is a minimum. This is negative, so it's maximum, and then this is positive, so it's a minimum. So this gives us the global, and this gives us the local, which is not the same value. Okay, any questions here? And then this is just doing the same thing, but for the maximum. Thanks for laughing. I know you all have done that at some point. Do you know the next time I'll do that? Later today. Okay, so then, this is just, we need a local maxima, and you can think through, this is just a figure I made to think through the thing, and we have this one here. So yeah, I think I just thought it through using what we've already solved for. So not a lot of extra to do this. Any questions? Nice, pretty pictures. I like to make fun of my job. Like, my job is mostly just drawing nice pictures.
Maybe this is, maybe I'm missing something, but why is
Okay.
the minimum that, thing that's barely under the x-axis instead of to the right where it goes way down?
Oh, I think the only thing you're missing is that my figure is bad. But there would be a local minima there. Oh, okay. Which would also be the global minima,
okay.
Yeah. Which I think is roughly what we found. So it's right around that point.
Okay.
So no, you're not missing anything, except that you can't see this part of the figure. What if we set this to -50? There we go. Who made these slides? My undergrads love that joke. I can break it out every class and they'll laugh. Okay. Maybe one day AI will write my slides, but we're not there yet. Okay. So question 3 was on simulation. So this was, this is sort of a contrived simplification of the example we did in class. So what we're doing are modeling these. This is a term I mean, I don't watch a lot of Premier League, but two-legged tie is just you have, I guess in in Major League Baseball, you play like against each other for a while. I don't watch baseball either, so why are we talking about sports? Good question.
You play against each other for a while.
Yeah, over and over again. In the English Premier League, you do that once. So you play at home and then away against the same team, called a two-leg tie. I'm not sure why it's called tie. Anyone know? I feel like we got a lot of sports people in this room, and
Kevin's not here today.
oh yeah, I'm sure he would know. So essentially what we're going to do is just model both of those things. So at home and away against the same team. And it's just going to be for Liverpool and Arsenal. And then we're just going to run this over and over again and then measure the total score. So this is just, so I'm just going to load the data set. I gave you this data set, I guess. I think I gave you this code to start. Did I give you? Yeah, that's probably all I gave you. So this is just how rude. This is just the teams themselves, and then here we're getting the alphas, which is the score for the offense, and then the delta is the sort of the measure for the defense. And I think these were given, let's see. Like I said, it's been a second since I've actually run this, which probably is true for you. So these are just the alphas and deltas, and then we had this expected goals and expected goals against. So what we're doing is just, we're going to construct the rate. So this is just the scoring rate, which you can get from the function here, and then we're just going to plug that in as the lambdas into the Poissons. Here I have the goals scored for Liverpool, and then the goals scored for Arsenal, which is just, how strong the offense is and how strong the defense is, and then we get the distribution. Okay, any questions here? So this is the score. And if you run this a bunch of times, you get different scores. Except that I have a random seed, so it's not going to be different. But if you take the seed out, you get different scores. Did I ask for a fixed random seed? Nope. Okay. Any questions? So the next thing we'll do is just run this 10,000 times. So all I'm doing here is just random seed for reproducibility, and then I have 10,000 as my sample size. Poisson using NP random just has a parameter that we can run a bunch of these at once. So this is one leg, and then this is another leg. I think if you did this with one match, that would also be fine. You'd just be like half of the observations. The main idea is just to get a large sample. So this is the total for Liverpool, which is the leg 1 plus leg 2, and then Arsenal is the total for across the two legs. And then what we're doing here is just if this is greater than the total for Liverpool is greater than the total for Arsenal, then we pick Liverpool and so on. And then, yeah, this is just a little more code to be able to do that. So I run this, and then I get the probability that Liverpool wins, which is the average. And then I get this thing. So it's, Liverpool is winning roughly 50% of the time, but slightly less. Any questions here? Not like a ton of novel stuff, right? We're just simulating 10,000 random samples and getting a mean. Which I think at this point in the class probably feels pretty simple, hopefully. If it doesn't, that's also fine. So then the next thing we're going to do is shock the games. So it's almost like we're saying we're going to play in the worst weather conditions possible, where everything becomes a little more random. If we made everything perfectly random, we would see both teams win about 50% of the time. So what this random parameter is doing, at least intuitively, is just adding noise, which pulls us closer to the 50%. So what I'm doing is just adding an epsilon. I'm adding that epsilon to the alphas. And I'm basically just putting that in the exponential. So this is almost identical to what we did with election shocks. And then everything else is exactly the same. So what this did is move us a little closer to 50, which is, actually it moved us a little away from 50. That's interesting, but that's what happened. Any questions here? So then we'll just plot this thing. So this is, did I give you the code to make this plot? Okay. Y'all are master students. I give this visualization code to my undergrads when we do these things. But y'all are grad students, so you must suffer through it. Hopefully it wasn't too much work. This is just a picture I would draw making a histogram of aggregate goal differences. So we're just taking, for each one of the games, it's going to be centered on 0 because they're close. And then, yeah, just centered on 0 like this. Okay. So my expectation is that this would, because we're already pretty close to 50-50, it's not going to do a lot, but it would move us closer to 50%. And it actually moved us kind of in the opposite direction slightly, at least with this random draw. We went from 0.46 to 0.459. So a slight move away from 50. Okay. Any questions here? Okay, so non-linear least squares. This was the last of the questions. So we have this Major League Baseball data set, and what we're trying to do is just estimate the parameters of of this distribution. So this is probably looks pretty familiar. This is like a Gaussian or a normal, and we just want to estimate the parameters of that model. This doesn't look normal, which I think a number of you had some questions about. This is sort of bell-shaped, but it's not exactly a normal. Sometimes when we estimate our models, like I would expect this to be close to normal, but not exactly normal. There are some pressures towards normality in ages. So this is yeah, the number of player seasons, and then age. But I think there are also lots of reasons for this to not be a normal distribution. But what we're going to try to do is try to get it close. So from this picture, you can go through and think about the different parameter values we could start with nonlinear least squares. And then behind the scenes, we're just going to throw Newton-Raphson at it and have it try to converge. So A0 is kind of the maximum. This would be about the center, and then the spread would just be something we could estimate directly. So here I'm just using those estimate values. Okay. Any questions here? So nice. Guess we should run this, right? And then here I'm just going to initialize and then define the objective function and then put that in the minimizer. And we'll use Neldermead, but you could use others. I think would work just as fine. And we can get the output here. This is that it converged. SSR is this number, which is challenging to interpret. But these are the estimates. So our sigma hat actually stayed about the same. Our mu hat increased, and the maximum height of our histogram, I guess that went down slightly. And then this is just a figure plotting the Gaussian on top, and you can see this doesn't quite line up, but it's a pretty good approximation for the distribution. Any questions here? And you can sort of realize why this might be overestimating the small values. If this were symmetric, young players, we'd see the number of player seasons sort of equal for young players, which you can sort of expect why this isn't true, because if you're young, you just haven't had as many opportunities to play for a long time. Okay. Any questions there? And then the last thing, this is just, we're plotting some of the parameter values and talking about where the model misses, which I think is clear from this figure. And there are no questions. So why don't we leave this here? I think we'll get out. Is this nice? 5 minutes early? These are like marathon sessions. Actually, my marathon time will be longer than this class. At least for this one.
How do you have to go to qualify for Boston?
Boston for my age group is, it's just over 3 hours. Like eventually I get it under 3 hours, but, which is, if you go to a treadmill, you hit 8.9 or 8.8. Yeah.
Speed 8.9?
Yeah, speed.
Wow.
It's like a 6:48 mile.
That's 48 seconds a mile.
Yes, 6 minutes and 48 seconds per mile.
And then you have to do it 26 times.
Yeah. I can't do that, but I believe I will one day.
We're gonna get an extra half an hour. Our age group for lunch is like 3:30, 3:25, something like that.
Okay, nice seeing everyone. I'll see you all on, so I'm gonna be in my office. I have a thing I'm probably going to from noon to 1, but I should be back a little after 1 till about 3, and then I'm skedaddling home to